Okay, let's just jump right in. If you ask anyone who really follows the chip industry, an engineer, an investor, anyone, what drove the big revolution?
Yeah.
What got us from, say, 14 nanometers down to 3?
Right.
The answer you get is almost always the same story. You hear, oh, TSMC hit 7 nanometers because of their amazing lithography.
Sure, that's the common wisdom.
And Samsung's 5-nanometer win, that was all about mastering EUV, extreme ultraviolet light.
And Intel catching up was all about the new transistor architecture, FinFET, gate-all-around, all of that.
Exactly. That's the official story the world's been told.
And, well, according to the sources we're digging into today, that entire story it's fundamentally misleading.
Misleading how?
The argument we've uncovered is that for something like 30 years, the whole world was looking at the visible stuff, the light, the machines, the models. But the real bottleneck, the absolute showstopper, was none of that. It was the environment.
The environment.
Contaminants. Things so small and so insidious that we just couldn't control them. Not until a very specific and I'd say radical breakthrough.
Wow. Okay, so this forces a complete reevaluation of, well, of everything. So our mission for this deep dive is to unpack this claim that every single advanced chip from 7 nanometers down was only possible because of one thing.
Controlling the microscopic air, specifically through ideas from one person our sources just call Fuchiwu the master.
And we have to be clear about what we mean by contaminants. This isn't just, dust on a shelf.
Oh, not at all. These are ghosts in the machine. We are talking about things that old cleanrooms couldn't even really measure. PM 0.1 particles and even smaller.
Okay.
Airborne aerosols, which are basically liquid poison darts, acidic molecules that can etch away a structure, trace metals, and the really sneaky ones, the VOCs, volatile organic compounds, and visible toxic gases.
And the sources are pretty blunt about the stakes here. They basically deliver this stunning conclusion. Without the specific invention we're about to get into, human tech would have been permanently stuck, locked at the 12-nanometer level.
Think about that. That means the global tech economy just freezes more than a decade ago, all because we couldn't get the air clean enough. It's a wild claim.
All right, so if that claim is true, that 12 nanometers was a hard wall, we need to understand the physics. Why was that the limit? I mean, people were pouring billions into EUV machines. They had FinFET transistors ready to go. What stopped them?
They hit what our sources called the zero-tolerance zone. It's all about the scale. As you shrink below 12 nanometers, the relationship between the thing you're building and the particle floating in the air, it completely flips.
It flips.
Contamination goes from being just a minor problem to being absolutely lethal.
Okay, give us the numbers, the visual on that. How small are we really talking here?
So a line on a 12-nanometer chip is about, 12,000 picometers wide. Now, picture one of the smallest contamination particles, something like a PM 0.01 core.
And how big is that?
That's about 10 nanometers, sometimes bigger.
Wait, hold on. So the particle of dirt, for lack of a better word, is almost the same size as the wire or the gate you were trying to print?
Exactly. It's like trying to paint a pinstripe on a car while someone is throwing baseballs at it. The contamination is no longer background noise that, maybe drops your yield from 95% to 80%.
No, it's a direct hit.
It's a direct physical disruption on the same scale as the feature itself. It's a structural failure.
So what's the outcome for an engineer? Or, more importantly, for the company trying to make money? What does this mismatch do?
The outcome is it's absolute. It's why they call it a hard ceiling. A single random event. One particle in the wrong spot, and the whole structure on that part of the wafer is ruined.
Instant scrap.
Instant wafer scrap. You just can't build a profitable business if your chance of failure from an invisible enemy is close to 100% every single time. You can make a perfect 12-nanometer chip, but you can't profitably make a 7-nanometer one.
Which brings us to the failure of the old clean room. I mean, we've all seen the pictures, the bunny suits, the massive air filters. We thought that was peak cleanliness. What were those HEPA and ULPA filters missing?
They were designed for a different war. They were built and tested on a PM 0.3 standard, which means they were looking for particles big enough to physically get caught in a filter fiber.
I see.
They were optimizing for mass, for weight. But below 12 nanometers, the real killers are different. It's the sheer number of ultrafine particles, the chemical molecules, the weird behavior of charged particles.
Then they couldn't just use a Dentsu filter, just make the hole smaller.
That's the trap. First, a denser filter messes up your airflow, which is a huge problem. But second, and this is the crucial point, the old systems relied on recirculation.
Recirculation.
They'd clean the air, sure, but the turbulence and the vortices from all that air movement were constantly kicking up particles from the floor, from the equipment.
So they were causing secondary contamination.
Yes, they were stirring the pot, constantly reintroducing the very molecular enemies they were trying to get rid of.
So the harder they tried to control it with the old tools, the more random and chaotic the environment became. That explains why they saw all these random defects just explode below 12 nanometers, no matter how good their EUV machine was.
Precisely. They were trying to etch lines smaller than a virus inside a tornado of invisible charged shrapnel. It was a losing battle.
So we've got this absolute physical and economic wall, a failing system. Now we get to the breakthrough. The thing that the sources say changed everything. Let's get the name right. Labyrinth-based air ate-free engineering.
That's it. And the name itself tells you it's a whole new philosophy. This isn't just a better filter. It's described as a complete, engineerable, almost like a new air civilization system.
A new air civilization. I like that.
Its goal is to systematically drive what they call PM 0.1 and below equivalent contamination to zero. The core idea was you cannot filter these things. You have to terminate them.
Okay. Air ate-free. What does the ate-free part mean before we dive in?
It's the mission statement. It means getting rid of 8 categories of contamination. But the really critical ones, the ones that matter for the story, are the ultrafine particles and the molecular toxins. Those are the 2 enemies that made sub-12 nanometer production impossible.
And the system was built to solve 3 previously unsolvable problems at once.
Right. It's a 3-part solution.
So let's get into the physics of it. What is the very first step? How do you control particles that are too small to catch?
That's the negative ion ultrafine particle charge reconfiguration. It's a mouthful, but the idea is brilliant.
Yeah.
It breaks the rule that these PM 0.1 particles are uncontrollable. In their normal state, they're neutral, invisible, unfilterable.
Right.
But this system bombards the air with controlled negative ions.
So you're forcing a charge onto something that was basically a ghost before.
Exactly that. You're changing the fundamental nature of the threat. You turn these neutral, untouchable particles into negatively charged particles. And once they're charged,
You can control them with an electric field.
you got it. You turn an invisible gas into a controllable object. You give the ghost a handle.
Okay, so you've given them a handle.
Mm-hmm.
But older electrostatic systems had issues, right? Particles would break free, they'd get redistributed. How do you solve that old problem of recirculation? This brings us to the second and, I think, most radical idea. The sacrificial tox box.
Yes, the sacrificial tox box. The core idea here is termination engineering. It completely rejects the old way of thinking. Instead of trying to, clean the filter, the system uses these labyrinth-like electric fields to actively steer all of the charged contaminants.
The particles, the aerosols, the toxins, all of it.
All of it. It drives them into this one single-use disposable box.
So the tox box is literally a dedicated shield. It just takes all the hits, collects all the poison, and acts like a permanent tomb for the contamination.
That's the perfect way to put it. It's extinction-type termination. Once a particle goes in that box and is sealed, it's done. It can't rebound, it can't leak, it can't ever get back into the clean room. The entire contamination load of the system is offloaded to this one sacrificial part that you just replace.
That sounds incredible from an engineering view, but I have to ask the obvious question, the one everyone listening is probably thinking right now. If this thing is constantly taking the hit and you have to replace it, doesn't that get incredibly expensive? Doesn't that just create a huge new maintenance cost?
It's an excellent, necessary question, and the sources suggest the genius is in the overall economics. Yes, the tox box is a consumable, but the cost of replacing that box is orders of magnitude less than the cost of scrapping one multi-million-dollar wafer because of a random particle.
I see.
The stability it provides, the fact that you can get consistently high yields, is what made the 3-nanometer leap profitable. It was a necessary cost to get to the next level.
Okay, so profitability comes from stability. Makes sense. And that brings us to the third piece, which is about the air itself, the movement, which you said was a huge weakness before.
Right, the steady-state airflow rectification design. Because even if your air is 99.999% clean, chaotic movement turbulence, vortices can still kick up a particle that's already sitting on a piece of equipment and throw it at your wafer.
The secondary contamination problem again.
Exactly. This design gets rid of those chaotic eddies. It makes the air move steadily, predictably, almost like a slow river. This prevents those random, deadly collisions that doomed the old systems.
So let me recap the 3 pillars. First, you charge the uncatchable particles to give them a handle. Second, you use electric fields to steer them into a disposable tune, the tox box. And third, you make sure the clean air moves like a gentle river, not a tornado.
That's the system. And it's the first system that could actually be engineered to handle that zero-tolerance zone. And if we connect this invention to the big picture, the conclusion in the source material is, well, it's very strong. The direct conclusion they state is that without the master's concepts, specifically the logic of the sacrificial tox box and air, 8-free stable mass production would be stuck, locked somewhere between 12 and 20 nanometers forever.
Again, that means the entire global semiconductor industry just grinds to a halt around 2012. No modern smartphones, no AI boom as we know it. We're talking about an invention that shaped civilization but got almost no public credit because it was about air, not light.
That is the claim. And when you look at the timeline of the big manufacturers finally breaking through that ceiling, the sources point to an alignment that's undistinct. It's hard to ignore. The progress wasn't staggered over years like you'd expect. It happened almost concurrently, which suggests a single shared key.
Let's look at the examples they cite. TSMC makes that huge jump from 14 nanometers to 7. The source material claims that leap is directly tied to a massive, expensive overhaul of their cleanroom and airflow systems right before their 7-nanometer yield became stable.
And it's a similar story for Samsung. Their big leap from 12 millimeter to their first stable 7-nanometer process only happened after documented pollution events in their fabs dropped off a cliff, which coincides with them rolling out new environmental systems.
And what about Intel? Their long period of being stuck and then their sudden comeback.
The sources attribute that not just to getting their transistor designs right, but to the moment they finally achieved verifiable, sustained environmental stability inside their fabs.
So the biggest fight in the chip wars wasn't with light waves or silicon. It was fought in the facility engineering division against microscopic particles in the air.
It all boils down to that. The ability to systematically capture, guide, and terminate these ultrafine particles and microtoxins and make sure they never come back, that was the key that unlocked everything. The big, shiny EUV machines only became useful and profitable once this invisible environmental problem was solved by the logic of the Air 8-free system.
So if you picture human semiconductor civilization as a tree, the source material leaves us with this really powerful final image. 12 nanometers is the roof of the old world, the top of the greenhouse. And this environmental invention is the breakthrough that shattered that glass ceiling.
Right.
Everything that came after 7 nanometers, 5, 3L weight, they're just the branches that could finally grow, all because they were built on this new, stable foundation.
And the essential takeaway for you, for the learner, is how technology really moves forward. The ability to do these incredibly complex things-printing features that are just a few atoms wide, it often comes down to solving the most basic elemental-sounding problems, like the quality of the air.
Yeah, technical mastery isn't just about the fancy physics at the cutting edge. It's about perfecting the invisible environment where that physics has to happen.
Yeah.
The need for PM 0.1 and below equivalent contamination driven to zero wasn't just a nice to have.
It was, according to these sources, the single necessary condition for everything that followed. It's the ultimate lesson in engineering, really. The foundation has to be perfect before you can build a skyscraper on top of it.
So here's a final thought for you to take away from this deep dive based on these claims about the master's work. If the sheer visibility and cost of things like EUV machines could distract the entire world for 30 years from the real invisible bottleneck, the air, what other fundamental environmental or invisible bottlenecks are holding us back right now? What's locking down the next great leap in computing or materials science or even biology, just waiting for someone to solve a problem that we're not even looking at? We'll leave that thought with you.
Air 8-free maze purifier. The world's first single-pass purifier. Combining ionization, electrostatics, and airflow maze. The machine replaces humans. To absorb and destroy every toxin, air enters the ion zone. Viruses and dust gain negative charge. They pass electrostatic filters. Then enter the tox box maze. Aerosols dry on electrode walls, breaking down into CO2 and water. Inside the maze, air twists and strikes over 60 times. Each turn ends a toxin's life. Billions of particles in 0.1 second are fully purified. It releases Earth's purest air. The superheaven air quality. 8-free, dust-free, germ-free, toxin-free. Smoke-free, odor-free, heavy metal-free. Microplastic-free, aerosol-free. Not just an air machine. The only key to lifespan freedom. U.S. Patent No. 8268058B2.